Intensity of light. The strength of the radiation from a light from a light source is measured using until called candela. Measured candela. Or candle power. The total energy from the light source, the total energy from the light source including heat and all electromagnetic radiations, both are, is called radiance. Radiance and is usually expressed in watts. Radiation expressed watts. Luminance. Luminance is measure of light strength. Light strength. What going to measuring? It is actually perceived by the human eye. Luminance perceived by the human eye. Radiance is a measure of the total output of the source. Radiance is measure of the total output of source. Luminance measure just a portion of the perceived. Total output of the source. Total output of the source. Luminance measures just a portion of the perceived. How much portion perceived? How much portion? This much portion perceived. This much portion, like this. Brightness is a subjective psychological measure. Brightness, psychological measure. Of perceived intensity. Brightness is practically impossible. Practically impossible to measure objectively. It is relative. For example, burning handle darkened room will appear bright. Darkened room will appear bright. It will not appear bright in full sunshine. Not full sunshine. The strength of the light diminishes in inverse square proportion to its distance from its source. The strength of light dimensions inverse square proportion to its distance from the source. Otherwise distance from the distance from the source. This effect accounts for the strength of light dimensions in inverse square proportion to its distance is the distance from its source, light source, light source, sorry, light source. This effect accounts for the need for high intensity projectors for showing multimedia productions on a screen to an audience. This effect accounts for the need for high intensity projectors for showing multimedia productions on a screen to an audience. Human light perception is sensitive but not linear. Human light perception is sensitive but not linear. Sampling. Both sounds and images can be considered as signals. Sounds, images, considered as signals. Signals only. This is sounds. Signals only. This is images. Images also signals. In one or two dimensions. One or two dimensions. Respectively, sound can be described as fluctuation of the acoustic pressure in time. Like this. Acoustic pressure. Up and down. Acoustic pressure. Acoustic pressure in time. While imaging are spatial distributions of values of luminance or color. While images are spatial distributions of values of luminance or color. The latter being described in RGB, HSP components. Any signal in order to be processed by numerical computing devices have to be reduced to a sequence of discrete samples. So little bit taken. That is the samples. Total sound are total images like this. And each sample must be represented using a finite number of bits. The first operation is called sampling. The second operation is called quantization of the domain of real numbers. D sounds. Sampling is for one-dimensional signals. Sampling is one-dimensional signals. The operation that transforms a continuous time signal, such as, for instance, the air pressure fluctuations at the entrance of the air canal, into a discrete time signal, continuous time signal to a discrete time signal, that is sequence of numbers. The discrete time signal gives the value of continuous time signal. Total continuous discrete time signals. This discrete continuous total to given total continuous time signals. Read at the intervals time seconds. Read at the and time seconds. The reciprocal of the sampling interval. The reciprocal of the sampling interval is sampling rate fs equal to 1 by t. 1 by time. In this module, we do not explain the theory of sampling. In this module, do not explain the theory of sampling, but We rather describe its manifestations. For a more extensive yet is accessible treatment, we point to the Introduction to Sound Processing. For purposes, the process of sampling a 1 minus D signal can be reduced to three facts and a theorem. Fact 1. Fact 1. The Fourier transform of a discrete time signal is a function called spectrum. The Fourier transform discrete time signal, discrete discrete time signal, discrete time signal is called spectrum, total spectrum of the continuous variable omega, and is periodic with the period 2 2 pi. Given a value omega, the Fourier transform expects complex numbers, complex number that can be interpreted as magnitude and phase. Magnitude, which magnitude, plus or minus, like that, and the phase, which angle, like that. Translation time of the sinusoidal component of frequency. Sinusoidal component of frequency. Fact 2. Sampling the continuous time signal x of t with the interval t, we get the discrete time signal x of n equal to x and t, which is the function of discrete variable n. Function of discrete variable n. Sampling the continuous time signal x of t with the interval t, this t, get the discrete time signal x of n equal to x of nt, which is a function of the discrete n variable. Fact 3. Sampling continuous time signal with the sampling rate f of s sampling rate f of s produce a discrete time signal whose frequency spectrum is periodic replications of the original signal, and the replication period fs replication period fs Fourier variable omega for functions of discrete variables is converted into the frequency variable f in hertz by means of w equal to omega divided by 2 pi t. That is okay. The figure 1 shows an example of frequency spectrum of a signal sampling frequency FSA. In the example, the continuous time signal had all and only the frequency components between f minus fb plus fb. The replicas of the original spectrum are sometimes called images. The replicas of the original spectrum are sometimes called images. Frequency spectrum of a sampled signal. This is continuous time signal. Totally. This is the discrete time signal. Frequency spectrum of sampled signal. Fs minus Fs minus Mp this side 0 Fp Fs divided to F in y axis is Xf. frequency